Derivation of IV characteristics. In order to obtain the relationship between the drain current of a MOSFET and its terminal voltages, we make two observations. First, consider a semiconductor bar carrying current I, figure A, if the charge density along the direction of current is QD coulombs per meter, and the voltage and the velocity of the charge is V meters per second, then I equal to QD into V. To understand why, we measure the total charge that passes through a cross section of the bar in unit time with a velocity V. All of the charge enclosed in V meters of the bar must flow through the cross section in 1 second. Figure B. Since the charge density is QD, the total charge in V meters equals QD into V. This lamina proves useful in analyzing semiconductor devices. Here you can see the figure. A, semiconductor bar carrying current I. B, snapshots of the carriers of 1 second apart. Here you can see the figure. Channel charge with A, equal source and drain voltages, B, unequal source and drain voltages. Second, consider an FET whose source and drain are connected to ground. Figure A. What is the charge density in the inversion layer? Since we assume the onset of inversion occurs at VGS equal to VTH, the inversion charge density produced by gate oxide capacitance is proportional to VGS minus VTH for VGS greater than equal to VTH. Any charge placed on the gate must be mirrored by the charge in the channel, yielding a uniform channel charge density. Charge per unit length equal to QD is equal to W C naught x VGS minus VTH, where Vox is multiplied by W to represent the total capacitance per unit length. Now suppose, as depicted in figure B, the drain voltage is greater than 0, since the channel potential varies from 0 at the source to VD at the drain. The local voltage difference between the gate and the channel varies from Vg to Vg minus Vd. Thus, the charge density at a point x along the channel can be written as Qdx is equal to Wc naught x Vgs minus Vx minus Vth, where Vx is the channel potential at x. From equation, the current is given by ID is equals to minus Wc naught x Vgs minus Vx minus Vth into V. Where the negative sign is inserted because the charge carriers are negative, and V denotes the velocity of the electrons in the channel. For semiconductors, V equal to nu E, where nu is the mobility of charge carriers and E is the electric field. Nothing that E of x is equal to minus dV by dx, and representing the mobility of electrons by nu n, we have ID equal to Wc naught x Vgs minus Vx minus Vth into nu x dVx by V dx subject to boundary condition V naught is equal to 0 and VL equal to VDS. While Vx can be easily found from this equation, the quantity of interest is in fact ID. Multiplying both sides by dV and performing integration, we obtain integral s equals 0 to L id dx equal to integral v equals 0 vds w c naught x nu x v gs minus vx minus v th dv. Since id is constant along the channel, id is equal to nu x c naught x w by L vgs minus vth vds minus 1 by 2 v square ds. Note that L is the effective channel length. Here you can see the figure drain current versus drain source voltage in triode region. Here you can see the figure ID VDS. Figure plots the parabolas given by equation for different values of VGS, indicating that the current capacity of the device increases with VGS. Calculating dou ID by dou VDS, the reader can show the peak of each parabola occurs at VDS equal to VGS minus VTH, and the peak current is ID max equal to 1 by 2 nu n C naught x W by L VGS minus VTH whole square. We call VGS minus VTH the overdrive voltage and W by L the aspect ratio. If VDS less than or equal to VGS minus VTH, we say the device operates in the triode region, sometimes called the effective voltage. This is also called the linear region. Equations serve as the foundation for analog CMOS design, describing the dependence of ID upon the constant of the technology nu and C naught x, the device dimensions W and L, and the gate and drain potentials with respect to the source. Note that the integration in equation assumes nu n and v th are independent of x, and the gate and the drain voltages and approximation that we will revisit in chapter 16. If in equation VDS less than 2 VGS minus VTH, we have ID similar to nu and C naught x W by L VGS minus VTH VDS. That is the drain current is a linear function of VDS. This is also evident from the characteristics of figure. For small VDS as shown in figure, each parabola can be approximated by a straight line. The linear relationship implies the path from the source to the drain can be represented by linear resistor equal to R on equal to 1 by nu n C naught x W by L VGS minus VTH. A MOSFET can therefore operate as a resistor whose value is controlled by the overdrive voltage so long as VDS less than 2 VGS minus VTH is conceptually illustrated in figure. Note that in contrast to bipolar transistors, a MOS device may be on even if it carries on. Even if it carries no. Here you can see the figure linear operation in deep triode region. Here you can see the figure MOSFET as a controlled linear resistor current with the condition VDS less than very much less than 2 VGS minus VTH. We say the device operates in deep triode region. The utility of MOSFETs as controllable resistors and hence switches plays a crucial role in many analog circuits. This is studied in chapter 12. What happens if in figure the drain source voltage is VGS minus VTH. In reality, the drain current does not follow the parabolic behavior of VDS greater than VGS minus VTH. In fact, as shown in figure, ID becomes relatively constant. We say the device operates in the saturation region. To understand this phenomenon, recall from equation that the local figure saturation of drain current. Note the difference between saturation in bipolar and MOS devices. Saturation region. Here you can see the figure, pinch of behavior. Density of inversion layer charge is proportional to VGS minus VS minus V of x minus VTH. Thus, if V of x approaches VGS minus VTH, then QD minus VTH, then the inversion. If V of x approaches VGS minus VTH, then QD of x drops to 0. In other words, as depicted in figure, if VDS is slightly greater than VGS minus VTH, then the inversion layer drops at S less than or equal to L, and we say that the channel is pinched off as VDS increases further. The point at which QD equals 0 gradually moves towards the source. Thus, some point along the channel, the local potential difference between the gate and the oxide silicon interface is not sufficient to support an inversion layer. With the above observations, we re-examine equation for a saturated device. Since QD is the density of mobile charge, integral on the left-hand side of equation must be taken from s equal to 0 to s equal to L dash, where L dash is the point at which QD drops to 0, and that on the right from V of x is equal to 0 to V of x equal to VGS minus VTH. As a result, ID equal to 1 by 2 nu n C naught x W by L dash VGS minus VTH whole square, indicating that ID is little dependent on VDS if L dash remains close to L. For PMOS devices, equations respectively written as ID is equal to minus nu P C naught x W by L VGS minus VTH VDS minus 1 by 2 V square DS, and ID is equals to minus 1 by 2 nu P C naught x W by L dash VGS minus VTH whole square. The negative sign appears here because we assume ID flows from the drain to the source, whereas holes flow in the reverse direction. Since the mobility of holes is about 1/2 to 1/4 of the mobility of electrons, PMOS devices suffer from lower current drive capacity. Here you can see the figure saturated MOSFETs operating as current sources. With the approximation L is similar to L dash, a saturation MOSFET can be used as a current source connected between the drain and the source. An figure. An important component in analog design. Note that the current sources inject current into ground or draw current from VDD. In other words, only one terminal of each current source is floating. Since a MOSFET operating in saturation produces a current in response to gate source overdrive voltage, we may define a figure of merit that indicates how well a device converts a voltage to a current. More specifically, since in processing signals we deal with changes in voltages and currents, we define the figure of merit as the change in the drain current divided by the change in the gate source voltage, called the transconductance, as denoted by Gm. This quantity is expressed as Gm equal to dou ID by dou VGS whole VDS constant is equal to nu n C naught x W by L VGS minus VTH. In a sense, Gm represents the sensitivity of device. For high Gm, a small change in VGS results in a large change in ID. Interestingly, Gm in the saturation region is equal to the inverse of R in deep triode region. The reader can prove that Gm can also be expressed as Gm equal to root over 2 nu n C naught x W by L ID is equal to 2 ID by VGS minus VTH. Plotted in figure, each of the above expressions prove useful in studying the behavior of Gm as a function of one parameter while the other parameters remains constant. For example, equation suggests that Gm increases with the overdrive if W by L is constant, whereas equation implies Gm decreases with the overdrive if ID is constant. The concept of transconductance. Here you can see the figure. MOS transconductance as a function of overdrive and drain current can also be applied to a device operating in this triode region, illustrated in the following example. The distinction between saturation and triode region can be confusing, especially for MOS devices. Intuitively, we note that the channel is pinched off if the difference between the gate and drain voltages is not sufficient to create an inversion layer, as depicted conceptually in figure. As Vg minus Vd of a NFET drops below VTH, pinch off occurs. Similarly, here you can see the figure conceptual visualization of saturation and triode regions. If Vd minus Vg of a PFAT is not large enough, less than mod VTHP, the device is saturated. Note that this view does not require knowledge of the source voltage. This means we must know a priori which terminal operates as the drain. Thank you.